Hi guys, we're going to look at the energy that's released when a radioisotope decays. So I've got a picture of a little nucleus here, and it decays into alpha and some new nucleus. The other thing that's given off here is energy, so we're going to talk about where that energy comes from. So it turns out if you get some scales and you put this guy, let's put a box around him so we know what he is. This is our alpha. And this is our, put a triangle around him. Now we know all the mass numbers and the atomic numbers add up, but if you were to get some amazing scales and put the box on one side, so the box is this nucleus here, and on the other side you've got the triangle and you've got the alpha. It turns out if you had the world's best scales, the box is slightly more massive, slightly more mass than the alpha plus that put together. Now, if you count the particles, they all add up. So what does it mean? What it means is, it means that the protons plus the neutrons before, they actually weigh more than, this is before, after, the protons plus the neutrons, of which there are the same amount, they weigh less. Now what the heck? We've got the same amount, but protons and neutrons that are all bound up in one nucleus weigh different amounts when they're bound up in two nucleuses by a fraction of an amount. A fraction of an amount. And the difference between these, one is bigger than the other, we call that the difference in mass, the change in mass. So what do we do with that? Once we've worked out this change in mass, how much heavier our before was than our after, we then use the famous equation E equals mc squared, which is really actually E equals the change in mass, c squared. So the change in mass is the difference before and after. Difference in mass. And c is the speed of light. And that is a big number. That is 3 by 10 to the 8, and then we square it. So a tiny, tiny mass times by 3 by 10 to the 8 squared becomes a huge amount of energy. And that's why our nuclear bombs and nuclear reactors give off so much energy with such a small change in mass. So let's do an example of that. So I've given you a plutonium isotope, which decays into uranium and an alpha particle. Now, the actual atoms of this weigh this much. They're tiny, 3.9 by 10 to the minus 25. That's 0.00025 zeros, 39 kgs. So each atom is each nucleus, minuscule. So what I do is I look at my befores and I look at my after. So my before is just polonium. So that's 3.9695 by 10 to the minus 25. And my afterwards, I'm going to add both of these together. So I'm going to get my calculator. 3.902995 e to the minus 25. That means by 10 to the minus 25. I'm going to add 6.6446 e to the minus 27. That's an even smaller number. The alpha particle is lighter than the other stuff. And that gives me 3.96941. Where have I gone? By 10 to the minus 25. So they don't weigh the same. 3.9, 3.9, 3.969, 3.969, 3.96955 is heavier than 3.96944. So there's a difference there. So this is the first thing. Look at the befores and afters. Now I'm going to come up here, I'm going to work out the change in mass. So I'm just going to get this final one, subtract the initial one. That equals 3.96944 by 10 to the minus 25 minus 3.96955 by 10 to the minus 25. And I get a very, very small amount, 1.09 by 10 to the minus 29, which makes sense. Minus 29 is much smaller than minus 25, and it accounts for it being in the decimal points here. kgs. Tiny. Then I can work out my energy from E equals mc squared. So 1.09 by 10 to the minus 29 times C is 3 by 10 to the 8, and that is squared, times 3 10 to the 8 squared. That gives me 9.81 by 10 to the minus 13 joules. Now that's a small number. That's my final answer, okay? That's how much I get out when each atom decays. Very, very small number, minus 13 joules, by 10 to the minus 13 joules. However, this is all I'm going to ask you to do in your exam or your test for this. But making meaning of this, and when you get a rock, you have something like, if you do chemistry, you have something like, what's Avogadro's number? 6 by 10 to the 23 atoms in a kg of a rock or sample. So that's how many atoms you have, and if each one of these is decaying and giving off this much energy, minus 13, but you have plus 23 atoms, you end up with something on the order of 10 to the power of 10 joules. Huge amounts. Huge amounts. So that's just making meaning of this. It seems like a small number, but minus 13 is about right, by 10 to the minus 13. It's a big amount of energy just for a single atom. You really, when you go to do these problems, you've really got to set them out and go through them one at a time. Work out the total masses before and afterwards. Work out the change in mass, then you go on with your E equals mc squared. This is the hardest problem that people find when we go to do our test next week. Okay, I should be back on Thursday, so I can certainly go through these with you as well. But good luck.